Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So today we are going to discuss the module Physics at Nanoscale from the paper Nanoscience and Nanotechnology first. So after completing this module, you will be able to learn first nanoscale and the dimension to call the nanostructure. Second, we will discuss about the physics and chemistry at nanoscale. Thirdly, we will discuss about the material properties, electrical properties, and optical properties at nanoscale. Lastly, we will also discuss about the magnetic and mechanical properties at nanoscale. So students, let us start with a basic introduction about the module. Nanoscience is generally described as the science of small, size-dependent variations in the properties of the materials are central to the progress of this discipline. So after learning the important quantum confinement effects, we will discuss the most exotic properties of the nanoscaled materials in this module. So what is nanoscale? The macroscopic properties of any material, for example the melting and the boiling point, etc., can be measured by examining the sample in conventionally convenient quantities under standard lab conditions. These quantities can vary for different materials as well as the purpose of investigations. One of the most often defined quantity is a mole, such that 1 mole of any substance consists of 6.022 multiplied by 10 to the power 23 molecules. Thus, if any property of 1 mole of the substance is measured, this value usually represents the average value of 6.022 multiplied by 10 to the power 23 molecules of that substance. It is often deduced that this value remains same regardless of the size of the group of molecules under investigation. However, this does not hold for all materials. That is, as the size of the material is decreased to reach nanoscale, the same material may demonstrate radically different properties. In other words, materials start demonstrating size-dependent properties after reaching the nano dimensions. This happens because matter at nanoscale does not follow Newtonian principles and quantum mechanics needs to be applied to describe the behavior of materials. So this will be explained in this module. What kind of small is this? So nanoscaled materials are considered to be consisting of clusters of atoms, molecules, not the single atoms, molecules. So for instance, if we have 8 hydrogen atoms or 3.5 gold atoms placed adjacent, forming a row, become 1 nanometer long. In this regard, the size of the nanomaterials is intermediate to a single atom or a molecule, and their bulk forms. At these dimensions, matter exhibits the novel properties. Therefore, nanomaterials offers the following opportunities. First, they can be used to improve the existing materials as well as to produce new materials with exceptional properties. Second, as nanomaterials have the size resembling that of the largest molecules present in nature, such as proteins, DNA, etc., they can be integrated into a device to interact with these molecules. So, owing to their nanoscaled dimensions, nanomaterials are more close to the individual atoms and molecules than to their bulk materials, and therefore their behavior is described using quantum mechanics. Quantum mechanics is the scientific model employed to describe the motion and the energy of individual atoms and electrons. The significant quantum effects and the properties relevant at nanoscale are described as: gravitational forces become negligible and electromagnetic forces becomes dominant. Second, we have the wave-particle duality. Third, tunneling. Fourth, quantum confinement. Fifth, quantization of energy. Sixth, random molecular motion assumes importance. Seventh, larger surface area to volume ratio. And lastly, we have the energy of confined electrons. So let us first discuss about the gravitational force, which becomes negligible and electromagnetic forces becomes dominant. At nanoscale, electromagnetic forces dominates where the gravitational forces are negligible. So according to this figure, the mass of the nanoscaled objects becomes very small. Gravitational force, which scales linearly with the mass of the particles, becomes negligible. Now, electromagnetic force is independent of the mass of the particles, and it is determined by the charge and the distance of the particles. It is strong even for the nano-sized particles. As an example, between two protons, electromagnetic force is 1036 times stronger than the gravitational force between them. Let us now discuss the second consequence, that is the wave-particle duality. For extremely small objects having very low mass, for example electron, wave nature becomes pronounced. Thus, an electron exhibits wave-like properties and its position can be described by the wave probability function. Next is the tunneling. Tunneling is an extremely important consequence in nanoscaled materials. As per the classical physics, an object can pass a potential barrier if its energy is greater than that of the barrier. Thus, if the object has energy lower than the barrier potential, the object cannot cross the barrier. In this case, there is zero probability of locating the object on other side of the potential barrier as shown in this figure. So as per the quantum physics, the object can tunnel through the barrier. Also, the thickness of the barrier is crucial in determining the tunneling probability of the particle. That is, the thickness of the barrier should be of the order of particle's wavelength. Thus, even if the object energy is lower than the potential of the barrier, there is a finite probability of locating the particle at the other side of the barrier. So, tunneling is an important quantum effect and forms the basic principle of scanning tunneling microscope (STM) used to image the nanostructured materials. Quantum confinement in nanostructured materials such as metals, electrons are confined in a space rather than free to move in the bulk of the material. Quantization of energy. Electrons can only exist at discrete energy levels. Quantum dots are the nanomaterials that displays the quantization of energy. Random molecular motion assumes importance. Above absolute zero, the molecules move owing to their kinetic energy. This is called as random molecular motion and is always present in the materials at a temperature above 0 Kelvin. So at macro scale, this motion is negligible in comparison to the size of the objects and thus do not influence the object's movement. However, at nanoscale, these motions are comparable to the particle's dimension and thus affect their behavior. Seventh is your large surface area to volume ratio. One of the distinguishing properties of the nanomaterials is that they have very large surface area. The smaller something is, the larger its surface area is compared to its volume. So this high surface to volume ratio is a very important characteristic of nanoparticles. This property will be described in detail in the subsequent sections. Let us now discuss about the last consequence, that is the energy of confined electrons. So, in this case, the nanocrystals where the energy levels of electrons do not remain continuous, as is the case with the bulk materials. Rather, owing to the confined electron wave functions, they become discrete, resulting in finite density of states. So these effects appear when the dimensions of the potential well approaches the de Broglie wavelength of the electrons, resulting in the change in energy levels. The effect is described as the quantum confinement, and consequently the nanocrystals are often called as the quantum dots. These effects influences the electrical, optical as well as the mechanical behavior of the material. So depending on the QD size, confined electrons have higher energy than the electrons in bulk materials. This shift in energy as shown in this figure, is given by delta E equal to n square h square by 8ma square. Now here n represents the principal quantum number, h is the Planck's constant, m is the effective mass, and a is the radius of the quantum dot. Let us now discuss the chemistry at nanoscale. Since a nanomaterial is formed of the cluster of atoms or a cluster of molecules, it follows that all types of bindings important in chemistry are also important at nanoscale. And these are, first is intramolecular bonding. These are also called as chemical interactions and involve changes in chemical structure of molecules. These include ionic, covalent, and metallic bonds. Next is your intermolecular bonding. These are the physical interactions causing no change in chemical structure of the molecule. These include iron-iron and iron dipole interactions, van der Waals interactions, hydrogen bonds, hydrophobic interactions, repulsive forces. So nanomaterials are formed of a variety of molecules joined together or larger molecules which takes 3D structures via intermolecular bonding such as macromolecules. Thus, nanoscience includes supramolecular chemistry as well. Additionally, intermolecular bonding plays a significant role in these macromolecules. Intermolecular bondings includes hydrogen and van der Waals interactions. Such bonds are individually weak. However, when they are present in large numbers, their total energy can be very large. As an example, a DNA molecule cross section is 2 mm, has numerous hydrogen bonds holding the two helices together. These interactions assume great significance in nanomaterials as their surface area is very large and numerous small forces apply on very large areas. Intermolecular bonds are essential to the structure of macromolecules, for example, proteins. They form their specific 3D structure which has specific biological functions. Any disturbance to these bonds may permanently affect their structure, which in turn may deteriorate their working. So, hydrophobic effect is another significant intermolecular interaction in nanoscience. This process is fundamentally driven by entropy. This property can be described as the ability of non-polar molecules to exist as clusters in water. Material properties at nanoscale. So the first property is the surface property. Surface properties influences the physical and the chemical properties of all the materials, whether they are in bulk or nanoscale form. So the surface performs several functions, such as they manage the inflow or outflow of the materials or energy. They can work as catalyst, etc. The science which investigates the chemical, physical, and biological properties of the surface is termed as surface science. Generally, the surface is regarded as the interface since it acts as a boundary between the material and its surroundings. So nanomaterials possesses large surface areas. This can be understood as follows and is explained in detail in this figure. When the bulk material is repeatedly divided into smaller and smaller pieces, total volume of all the pieces taken together does not change, while the surface area considerably increases. Thus, the surface area to volume ratio is greatly enhanced. So, the importance of surface atoms is that the chemical groups present at the surface interface of the material influence its properties. Example, the catalysis, electronic conduction, adhesion, gas storage, etc. Since in nanomaterials, majority of the atoms are present at their surface, they exhibit the enhanced surface activities. This makes nanomaterials particularly useful in catalytic reactions, detection reactions, including the sensing of a specific compound, etc., which requires the physical adsorption of particular species at material's surface. Additionally, properties like melting point are also affected by the size of the particle. Nano-sized particles of a material have lower melting point than their bulk forms. This is because it is easy to remove the surface atoms as they are in contact with fewer atoms of the material. Thus, the energy required to overcome the intermolecular forces holding the atoms is low, leading to lower melting point. As an example, bulk cadmium selenide melts at 1678 Kelvin, whereas a 3 nanometer cadmium selenide crystal melts at 700 Kelvin. The next is the shape also matters. So for a given volume, the surface area also depends upon the material's shape as shown in this figure between a sphere and cube with equal volumes. So the surface area of the cube is larger. Consequently, apart from the size, shape of the material is also significant. Energy utilization. Artificial catalysts are usually produced by fixing metal particles over oxide surfaces. These are not energy efficient. The active surface of a catalyst is very important in catalyzing processes since higher surface implies higher surface activity. As the size of catalyst is reduced, its active surface area increases. Second is the detection or the sensing. The detection of a specific chemical or biological species from a mixture is the basic principle of operation of sensing devices. So, in this case, similar to the catalysis sensing, it is also surface interface phenomenon. The rate, specificity, and accuracy of this reaction can be greatly enhanced by the nanomaterials. Enhanced surface area in nanomaterials provides more active sites available for detection, resulting in rapid detection. So the detection limit is also lowered over here. Further, as the nanomaterials with specific surface behavior can be easily designed at molecular level, the active sites on the material surface can act as the lock to detect the specific molecule. Electrical properties. Quantum confinement and its effect on the electrical properties of the materials. Quantum confinement results in increase in the energy bandgap of the material as shown in this figure. Additionally, at nanoscale dimensions, as the energy level becomes quantized, thus the bandgap overlap in the metals disappears and a bandgap emerges. Thus, some metals behaves as semiconductors at nanoscale. The increase in the bandgap energy implies that more energy can be absorbed by the material. Higher energies means shorter wavelength or blue shift. A nanomaterial will emit the fluorescent light of higher wavelength, resulting in blue shift. So by adjusting the size of the nanoparticle, its absorption and emission can be tuned over a wide wavelength range. Optical properties. Nano-sized semiconductors have quantized energy states, therefore the conduction and the valence bands split up and becomes discretized. Charge transfer occurs between these discrete levels, so only wavelengths of a certain dimension are absorbed, and as a consequence, emission is also monochromatic. Quantum confinement causes the energy of the bandgap to increase, therefore, more energy is needed to be absorbed by the bandgap of the material. So this figure shows the 10 distinguishable emission colors of zinc sulfide capped cadmium selenide quantum dots excited by a near UV lamp. So tuning the size of the semiconductor nanocrystal is a means to tune the bandgap, and therefore the wavelength absorbed emitted by the crystal. Consequently, the same material, such as cadmium selenide, emits different colors depending on its size. So let us now discuss about the magnetic properties. Nanostructuring of bulk magnetic materials can be used to alter the magnetization curve of a material, resulting in soft or hard magnets with improved properties. Generally, the magnetic behavior of a material depends on the structure of the material and on its temperature. So, for experiencing a magnetic field, a material must have a non-zero spin. So, the transition size of classically expected magnetic domains, that is around 1 micron, when the size of the magnet is reduced, the number of surface atoms becomes a significant portion of the total number of atoms. Surface effect becomes important and quantum effects begins to dominate. As the size of these domains is reduced to nanoscale, the materials exhibit novel properties because of quantum confinement, like the giant magnetoresistance effect GME. So this is a fundamental nano effect which is now being used in modern data storage devices. Let us now discuss the mechanical properties. Some nanomaterials have inherent exceptional mechanical properties depending on their structure. One such material is carbon nanotubes, which are extremely small tubes having the same honeycomb structure of graphite but with different properties than it as shown in this figure. So CNTs can be 100 times stronger than steel but 6 times lighter than it. So students, let us now summarize what we have learned in this module. Firstly, we discussed about the nanoscale, that is physics at nanoscale and the dimensions to call the nanostructure. Secondly, we discussed about the physics and chemistry at nanoscale. Thirdly, the material properties, the electrical properties and the optical properties were discussed in detail at nanoscale, means how they changes at nanoscale dimensions. Lastly, the magnetic and mechanical properties and their changes, the phenomena leading to this change, was also discussed in this module. Thank you.